this lecture and further few lectures I will be devoting on material and heat balance in roasting. I will be solving few problems and giving few problems for your practice. So, let us see first of all how these problems on roasting are tackled. So, I am taking problem number 1, like say ore concentrate of the composition 6% copper, 35% sulfur and rest is gangue is roasted with oxygen, of course derived from air, Now, here oxygen is 200% excess. This means we are using 300% theoretical air for the roasting process. Now, in the ore concentrate, all copper is in form of CuFeS2 and sulfur also forms FeS2 mineral. So, this is what is given. Now, remember the composition of the concentrate is given in terms of ultimate analysis. It is in terms of elemental analysis, and hence you should not do 6 plus 35 and you subtract this from 100, that will give you the amount of gangue. No, it will be wrong. So, that point is to be clear. Number 2, the roasting takes around 300% theoretical air, that is what given in the problem. So, now first you have to find out, say calculate say amount of mineral and gangue in ore concentrate. Second, you have to calculate theoretical amount of oxygen. Now, remember, you can also call theoretical amount of oxygen or stoichiometric amount of oxygen, they mean the same thing. That means, you have to write down a balanced chemical equation, and then whatever you calculate based on the balanced chemical equation, as I have illustrated in the lecture on the stoichiometry, that is meant by theoretical amount of in this particular case of oxygen. Third, you have to calculate actual amount of air supplied. Fourth, you have to calculate volume of SO2 and of course, amount of Fe2O3. This is a relatively very simple problem. I am starting with a simple problem. So, let us go with the calculation. So, let me say solution. Let me illustrate by a box which tells you about the inputs and outputs. So, here is the box. I have now 6% copper, 35% sulfur, and I have the gangue. So, also it is stated in the problem that the gangue does not contain copper, sulfur or iron. Please understand that also, that the gangue does not contain copper, sulfur or iron. So, this is the roasting is going on, here is the roasting. So, we have to find out number 1, the amount of mineral at gangue. So, let us consider first of all basis 1000 kg ore, 1000 kg ore, and the atomic weights that I will be using for copper I am using 64, for iron I will be using 56, for sulfur I will be using 32, and for oxygen I will be using 16. That is what I am going to do it. So, first of all we have to find out the amount of mineral and gangue, and it is said that all copper is in the form of CuFeS2 and sulfur and some FeS2 is also forming. So, first we can find out the say percent CuFeS2, that will be equal to 6 into 184 upon 64, that will be equal to 17.25%. Now, we have to find out sulfur in CuFeS2, that will come to be equal to 6%, you can find out by percentage, and then that means 29% sulfur is as FeS2 mineral. So, now straight away I can write down. So, I can straight away write down this 29% sulfur is FeS2 is mineral. So, therefore, the percent FeS2 will be equal to how much? Percent FeS2 will be equal to 54.375%, because 29 into 88 by 32, that will be the percent FeS2. So, now I can calculate the amount. So, the CuFeS2, then FeS2 and then gangue. So, CuFeS2 is 17.25%, FeS2 is 54.375%, and rest gangue of course 100 minus this, that will be 28.375%. So, in terms of their weight, I have here now 172.5 kg of the 100 kg ore is the basis. This will be 543.75 kg is FeS2 and 283.75 kg, this is the gangue, and this is the answer for 1. That is how you will be calculating the amount of mineral. Now, next it says theoretical amount of oxygen. Now, theoretical amount of oxygen can be determined by writing the balance roasting reaction. So, in this case the oxidation will occur of FeS2 and that of chalcopyrite, that is CuFeS2. So, all that we have to write down the equation or the balance chemical equation, and from there we can find out the amount of oxygen. So, the roasting reactions are say 4 FeS2 plus 11 O2, that is equal to 2 Fe2O3 2Fe2O3 plus 8SO2. Similarly, for CuFeS2, 4CuFeS2 plus 13O2, that will be equal to 4CuO plus 2Fe2O3 plus 8SO2. So, these are the roasting reactions, and there is no other mineral present in the ore concentrate that requires oxygen. So, all that we have to find out the moles of FeS2 and the moles of CuFeS2, and then straight away you know how much amount of oxygen would be required. Now, remember, I am rather very comfortable by solving the problem by converting into moles. However, you can do with kg, whichever way you want to do it, all that we are interested in the answer. So, I am very much comfortable if I convert these things into mole and then solve the problem. So, I will convert the moles. So, moles of CuFeS2, that comes out to be equal to 0.9375, and moles of FeS2 that comes out to be equal to 4.5313. Straight away kg divided by molecular weight, you have the moles. So, I can straight away find out from here the stoichiometric amount of oxygen, or you can also call theoretical amount of oxygen, whichever way you want to understand, that is the oxygen which is required for the equation this and for the equation this one. So, you see, according to equation 1, 4 moles of FeS2 requires 11 moles of oxygen. According to equation of roasting CuFeS2 and oxygen, 4 moles of chalcopyrite require 13 moles of oxygen. So, straight away I can calculate the moles of CuFeS2 0.9375 multiply by 11 by 4, then I will be getting here 3.047 moles of oxygen, and here I will be getting 12.461 moles of oxygen that will be required. So, the total moles of oxygen, total moles of course, stoichiometry oxygen, that will be 15.508. So, then stoichiometric amount of oxygen that is supplied multiplied by 22.4, then this is equal to 347.4 meter cube. This is what is asked in 2, where you are required to calculate theoretical amount of oxygen. Now, you have to calculate actual amount of air. So, 3. So, actual amount of air is 300% that of theoretical air. So, actual air supplied, I mean to say actual air supplied, that will be equal to 4962.56 meter cube. Now, here it is important to remember that 1 kg mole is equal to 22.4 meter cube at 1 atm and 273 Kelvin. As such, this value is at 1 atm and 273 Kelvin. That is what is important. Now, next you have to calculate volume of SO2 and amount of Fe2O3. So, we can calculate, say, amount of Fe2O3 well, you can just calculate, because the equations are there, which says on roasting of FeS2, 2 moles of Fe2O3 are forming, on roasting of CuFeS2, 2 moles of Fe2O3 are forming. So, you can do that, and amount of Fe2O3 will come 437.5 kg. Similarly, amount of SO2, so if you see the balanced chemical equation, that will be 4.531 into 2 plus 2 into 0.9375. Now, volume of SO2, that will be equal to 4.531 into 2 plus 2 into 0.9375 multiply by 22.4. Mind you, this is in kg moles. Now, this is in meter cube. So, this amount comes 245 meter cube. So, this is the answer for fourth one, and this is also the answer for fourth one. Now, addition, what I have done, we can also get the information of the volume of gases and their composition. So, if you want to know the volume of gases, there is just an additional calculation that I am doing, because the output of the roasting is the roast product plus gases. So, volume of gases one can find out, say SO2 we have already determined 245 meter cube, then the nitrogen, that will be equal to 3920 meter cube. Now, since you use excess air, so there will be excess oxygen, there will be also in the gases, and this will be equal to 695 meter cube. So, the total amount of gases that will be forming around 4860 meter cube. So, as such their percent, say SO2 will be 5%, N2 will be 80.7% and oxygen is 14.3%. So, that is how this problem can be understood and can be solved. I will again illustrate with one more problem, that is little detailed problem. Let us see that problem number 2. So, the problem number 2, let me first of all make the statement. Consider roasting of copper concentrate. Copper concentrate of composition copper 8.8%, SiO2 19%, iron 29.7%, sulfur 36.9%, Al2O3 5.3%, calcium oxide 0.3%. Roast product has the following analysis, Now, the roast product contains copper 11.1%, SiO2 24%, iron 37.6%, sulfur 10%, Al2O3 6.7%, calcium oxide 0.4% and oxygen 10.2%. Now, mind you, roast product, the analysis shows oxygen is also there, but always remember, as I said, the ore concentrate, though elemental analysis are given, but the ore concentrate always contain the so called minerals. Similarly, in the roast product also the analysis of copper, iron, sulfur is given, it does not mean it contains copper, iron or sulfur as it is, but it is always in the form of minerals. So, that is an important thing you should understand. Now, some conditions are given, say copper in the Roche product, copper in the Roche product is as Cu2s, and note iron is partly oxidized, as Fe2O3 and partly as Fe3O4. Second thing is that the air used is 5000 meter cube expressed at 1 atmosphere and 273 Kelvin per ton of ore concentrate. Also fuel is also used. So, fuel burned in the roasting process is 5 kg per ton of ore concentrate. And that is fuel burned is 5 kg per ton of concentrate, and it is here pure carbon. Fuel you consider pure carbon, and another condition is given of the sulfur oxidized oxidized 85% goes to SO2 and 15% goes to SO3. These are the conditions. Now, what you have to do it? You have to find, of course, per ton of concentrate, find per ton of concentrate A, you have to find out weight of roasted ore, weight of roasted ore. B, percent elimination of sulfur. C, volume and composition of gases, volume and composition of gases. And finally, to find excess air for burning carbon and roasting. Note, gases produced due to roasting and due to burning of carbon, they mix in the reactor and the mixture goes out of the system. That is also thing I thought I must mention it over here. Now, say first of all, I will straight away we can go to the solution of the problem. the first we have to calculate weight of roasted ore per ton of concentrate. Now, here let us consider x kg roasted ore, x kg roasted ore, or you can call roast product, they are one in the same thing. Now, remember, you recall in the roasting I have said that roasting takes place in the solid state. There is no melting type of anything occurs. The reactants are in the solid state, the products are also in the solid state, number 1. Number 2, roasting is essentially an oxidizing process. Now, when we call this is an oxidizing process, then all other oxides like SiO2, Al2O3, they are not oxidized. That means, whatever SiO2 in the ore concentrate, it will be totally available in the roast product. Whatever Al2O3 will be in the concentrate, the same amount, the same thing will also be available in the roast product. Though their amount will be different, the percentage will also be different because the weights will be different. But as regards the copper or iron or sulfur, they will be changing because of oxidation process. So, in order to solve such problem, you have to always catch hold of that particular mineral which is not undergoing any chemical reaction, number 1. Number 2, which is not undergoing in the process of formation of compound. Now, in this particular problem and several problems which will be coming now to you, the SiO2 and Al2O3, they do not form any chemical compound, they do not react at all. Also in this chain, calcium oxide is also another compound which neither react nor forms a chemical compound. But you can also do now the material balance. You can say SiO2, say I can write down SiO2 in the ore concentrate, SiO2 in the ore concentrate that should be equal to SiO2 in the roast product. That should be equal to SiO2 in the roast product. Now, our basis is 1000 kg because per ton you have to calculate. So, SiO2 in the ore concentrate, that is equal to SiO2 in the roast product, or you can also take Al2O3 in the roast product or Al2O3 in the roast product, or sorry, Al2O3 in the ore concentrate, that should also be equal to Al2O3 in the roast product, in the roast product. Here calcium oxide in the ore concentrate should also be equal to the calcium oxide in the roast product, but the problem with the calcium oxide is that the analysis is mostly rounded off and the percentage calcium oxide is very, very small. So, the balance which is, if it is done by taking calcium oxide in the account, it is liable to be error. That is why my suggestion would be to take SiO2 and Al2O3 as the balance and to do this in order to find out the weight of roasted ore. So, if you do that, we do either Al2O3 or SiO2 balance, the value of x, it comes to be equal to 791 kg. This is the answer for part A. Now, second we have to calculate percentage elimination of sulfur and so on, volume and percentage composition of the gases and excess air and so on. So, second we have to calculate now, B part we have to see. Now, since it is said that copper is as Cu2s, copper is as Cu2s. So, amount of Cu2s, amount of Cu2s, that will be equal to 0.111 into 791 into 160 divided by 128. So, amount of Cu2s that will be equal to 109.75 kg. Now, what I am determining? I am determining the composition of the roast product. The weight we have determined 791 kg. So, it will have Cu2 as this one. Now, the problem says iron is partly oxidized to Fe2O3 and partly oxidized to Fe3O4. Now, in order to know how much iron has gone to Fe2O3 or Fe3O4, we have to know, we have to do the sulfur balance also. So, sulfur in roasted ore that is equal to 79.1 kg. So, therefore, sulfur with iron because the sulfur in the roasted ore can go either with copper or with iron, and there is no other taker of sulfur. So, Cu2s we have already determined. So, if I subtract the amount of sulfur that has gone with Cu2s from the total sulfur contained in the roasted ore, then I will know sulfur with iron, and that is exactly what I am going to do. 79.1 minus 32 upon 160 into 109.75. So, that will give me 57.15 kg sulfur is with the iron. So, therefore, I can find out now amount of FeS that will be equal to 157.16 kg. Now, it also says that some amount of iron is oxidized to Fe2O3 and some amount to Fe3O4. Now, we have to know how much amount of iron now remaining, because some iron has gone to the formation of FeS. So, the iron which forms Fe2O3 and Fe3O4, that will be equal to total iron is 297 minus 157.16 is the FeS amount, divide by 88 into 56. So, this particular iron is with the FeS. So, if I subtract that, then I will be getting 197 kg. Now, what is this 197 kg? Now, this 197 kg of iron is forming Fe2O3 and Fe3O4. Now, we have to find out what is the weight of Fe2O3 and Fe3O4. Now, here comes little bit of thinking, a conceptual thinking. Now, if you look the analysis of roast ore, the roast ore says it contains 10% oxygen. Now, if you again look down very seriously the roasted ore, you will find that the roast ore free oxygen cannot be there if iron is there. So, iron can be either in the form of FeS or in the form of Fe2O3 and Fe3O4. So, here the clue for solving this particular problem is that 10% oxygen is given to you, which is present in the roasted product, roasted ore or roast ore, one and the same thing. That means, the 10% oxygen is combining with Fe2O3 and Fe3O4. So, I can form two equations. I know the amount of iron which is going to Fe2O3 and Fe3O4. I know now amount of oxygen which is going to Fe2O3 and Fe3O4. So, if I form two simultaneous equations, I can solve and I can get their respective amounts, right. So, that is what I am going to do it. So, let us consider now, let x kg Fe2O3 and y kg Fe3O4. This is what the thing, x kg Fe2O3 and y kg Fe3O4, hint I already given to you. So, what we have to do? Have you gotten what I am going to do now? Now, I am going to do, first I will do the iron balance. First I will do the iron balance, and iron balance will give me 0.7x plus 0.72y, that is equal to 197. Next, what I am going to do? This is my equation 1. Now, what I am going to do then next? Probably you got a hint, that is I will be doing oxygen balance. I will be doing oxygen balance. Now, if I do oxygen balance, it comes 0.3 x plus 0.28 y, that is equal to 81. This is my equation number 2. Now, I believe you must be an expert in solving these two simultaneous equations, x and y, two variables, two equations you can find out. So, x, it comes out to be equal to 158 kg, which is the amount of Fe2O3, and y, that will be equal to 120 kg. This will be amount of Fe3O4. Now, this particular problem is bit tricky, but if you think one gets the feel how to do this particular problem or the problem which will come them next. So, now the problem says, or some of the problems on roasting, that may also tell you that find out the proximate analysis of the roast product. There are two types of analysis, one is the ultimate analysis, another is the proximate analysis. In the ultimate analysis, we report the elemental analysis, but when we say report proximate analysis, that means you have to report the analysis in terms of percentage minerals. So, that is what the proximate analysis mean. So, proximate analysis of roast product, proximate analysis of roast product, that now we know all the product. Now, all SiO2, needless to say, all SiO2 of the ore concentrate will enter into roast product. All Al2O3 of the ore concentrate will enter into roast product. All calcium oxide will enter into roast product. So, we have known now all the weights. So, I can write down Cu2S, that is equal to 109.75, Al2O3 53, these are all in kg, this is in kg, SiO2 equal to 190 kg, CaO 3.2 kg, FES 157.16 kg, Fe2O3 just now we have find out 158 kg, and Fe3O4 that is equal to 120 kg. You sum total, and this sum total will give you 791 kg. If you want to find out percentage, it is very easy to find out the percentage of each and everything. Now, this is about what is asked. Now, you have to find out the volume and percentage composition of gases. So, let us find out now volume and percent composition of gases. We have to find now volume and composition of gases. Composition of gases. Now, here it is also important, that is which gases will form. Now, air used is given to you 5000 cubic meter per ton of ore. We do not know whether it is excess air or it is just theoretical amount of air, whatever it is. So, at the moment we can say only that the gases will be comprising of SO2 and nitrogen, because when air is used for roasting, nitrogen has to be there, because nitrogen is not reacting anywhere. Whether the exit gases will have excess oxygen or not, In this particular problem, we have to see or we have to find out whether there will be excess oxygen or not. Now, how do we go ahead? So, let us do little bit of exercise. So, first you have to find out sulfur oxidized to gases, sulfur oxidized to gases, that is equal to 369 is the total amount of sulfur that is sulfide. In the Roche product it is 79.1. So, oxidized into gases. So, if I divide by 32, then I will be getting 9.059 kg moles. That has gone to the gases. Now, the problem says 85% to SO2 and 15% to SO3. Now, have you understood what I am trying to do? I am now trying to do how much amount of stoichiometric amount of oxygen would have been required if I want to roast 1000 kg of ore concentrate to the composition that we have found out. If I calculate the stoichiometric amount of oxygen or stoichiometric amount of air and then I compare with the amount of air that is used in the process, then I will be knowing whether the roasting process is with excess air or stoichiometric amount of air. So, for that I have to find out what are those roasting reactions or where oxidation has taken place. So, one oxidation is sulfur to SO2 and SO3 is also forming. So, it is telling now here we can say now sulfur oxidized to SO2, that will be equal to 0.85 into 9.059, that is equal to 7.70 kg moles. Then sulfur oxidized to SO3, that will be equal to, of course, you can subtract this one, this or whichever way. I can also put it 0.15 into 9.059, that should give the same thing which I am going to write 1.36 kg moles. Now, we have to see what other oxidation reactions. So, I will write down now all the oxidation reactions seeing the problem. The oxidation reactions are S plus O2, that is equal to SO2, S plus 1.5 O2, that is equal to SO3. Now, you know you have to list all oxidation reaction 2Fe plus 3 by 2 O2, that is equal to Fe2O3, then 3 Fe plus 2 O2, that is equal to Fe3O4. Then there one more reaction will take place because you are combusting carbon and 5 kg per ton of ore. So, carbon plus oxygen, that is equal to CO2. So, these are all the oxidation reaction that is occurring in this particular problem. So, we have to find out the stoichiometric oxygen required for all these reactions, that is only we can find out. So, for SO2 and SO3 we can straight away find out 1 mole sulfur, 1 mole oxygen, 1 mole SO2 and so on, 1 mole sulfur, 1.5 moles of oxygen SO3 and so on. So, I will be writing down now stoichiometric oxygen required, stoichiometric oxygen required. Now, repeatedly I am telling you, if I say stoichiometric or I say theoretical amount, it one and the same thing. So, that will be equal to 7.70 plus 1.36 into 1.5 plus 158 upon 160 into 1.5 plus 120 upon 232 into 2 plus 5 upon 12. Now, this is for S to SO2, this is for S to SO3 oxygen required, this is for iron to Fe2O3, this is for iron to Fe3O4 and this one is for C to CO2. So, this total that is equal to 12.667 kg moles. So, now we know that much amount of stoichiometric amount of oxygen will be required to carry out the roasting and burning of carbon, both reactions. Now, we are very clear that this much amount of oxygen would have been required if stoichiometric amount of air would have been used for roasting as well as for burning of carbon. So, now let us see how much amount of oxygen is supplied actually. So, actual oxygen supplied, how will you find out? I have given you the total amount of air, that is 5000 meter cube. I multiply by 0.21, this is a meter cube of oxygen, and if I divide by 22.4 meter cube, then I will be getting 46.875 kg moles. What does it mean? That means, we have supplied 46.875 kg moles of oxygen to carry out roasting and combustion reaction. We were requiring only 12.667 kg moles of oxygen. Therefore, the system has excess oxygen in the roast gases. So, therefore, excess oxygen in gases, that will be equal to 46.875 minus 12.667, that will be equal to 34.21 kg mole. Now, this is the gases will also have nitrogen. Remember, nitrogen is the only gas which is inert, it does not take part in any reaction. So, therefore, the nitrogen in the system can be straightaway find out 5000 into 0.79 upon 22.4, that will be equal to 176.34 kg moles. So, my dear friends, that is how the amount and that is how the volume of gases are calculated. Remember, and it is always there that is the key to solution of these problems is just consider stoichiometric amount of oxygen, because that is what you can calculate and then proceed with the problem. So, now we can make the problem complete. So, volume of gases and composition, we can find out both of them together, as for example, SO2, SO3, O2, N2 and carbon dioxide. So, here that are in kg moles, 7.70, 1.36, 34.21, 176.34 and 0.42. This total it makes 220.03. Now, percentage I can always calculate, divide by this thing, straight away you can do it, 3.50, 0.63, 15.54, 80.14 and 0.19. I will like to draw your attention on the nitrogen content of the gases which are going out of the system. Remember, though we have not performed at the moment heat balance, but you can understand now the heat which is taken out by the inert gases. Now, here nitrogen is inert, you are carrying out roasting for example, 1000 degree Celsius or 900 degree Celsius. So, this 80.14% of nitrogen will carry a large amount of heat from the roasting reactor. So, that is what the use of air, how much amount of excess air you will be using, it is a very, very important thing in case of pyrometallurgical extraction, where oxygen for oxidation is derived from air. Remember, so nitrogen is a substantial percentage and it will take substantial amount of heat out of the heat that is produced in the reactor. So, this is an important thing to understand the role of air, the control of air, because you are deriving oxygen from air and air contains 21% oxygen and 79% nitrogen. So, this is the percentage. Now, we have to find out volume of gases. Volume of gases, that is straight away you can find out 220.03 into 22.4, that will be equal to 4928.67 meter cube. Mind you, 1 atmosphere and 273 Kelvin. Also, you must have noted in this particular problem that amount of air is more or less same to that amount of flue gas. You are seeing amount of air was 5000 meter cube, here 4928.67 meter cube, because part of the sulfur has gone to the Cu2s and FES. So, this is what. Now, next thing you have to calculate excess air. To calculate excess air, and the excess air will be straight away you can calculate 34.21 divided by 12.667 into 100, that will be equal to 273.7%. Now, in general always excess air is calculated in terms of the theoretical air. So, excess air will be either you say excess air upon theoretical air or actual air minus stoichiometric amount of air divided by theoretical amount of air into 100, that will be excess air in percent, or you can also report the excess air in terms of fraction, whichever way you want to call it. But excess air is always reported in terms of percentage theoretical air.